Okay, we actually have already gone through most of this by what we've just done, but the topic here in the last few slides in chapter 4 is solids and liquids heat capacity. Obviously, we've already dealt with it a little bit because we were at the problem, but all I'm saying is that the change in internal energy, the account balance in the brass, for example, is just the heat capacity times the change in temperature. As if you can quantify it this way. Okay, now enthalpy is U plus PV. And so if you take the differential of both sides, then you get DH, du on this side, but the differential of a product, what you have to do is hold one constant, differentiate the other, then hold the opposite one constant and differentiate the previous one. Right? Anyway, solids and liquids don't change their volume much when they undergo thermal energy changes. And so this term is approximately zero. So you're left with du VdP. And so if we then consider a macroscopic change in enthalpy from basically this equation, it would be delta U plus V delta P, because the only thing that changed appreciably is the pressure, the internal energy, and enthalpy. And so then you end up with the average heat capacity times delta T, just what we had before for delta U. But then VdP, this term is approximately zero. In other words, it's small by comparison to this term. And so basically this is just a mathematical way of proving that changes in enthalpy and changes in internal energy are approximately equal for solids and liquids. It's just some average heat capacity times delta T. Now that's not an average CP or CV. That's just an average heat capacity because even the heat capacity of solids and liquids varies as a function of temperature. Typically, they have different heat capacities at higher temperatures. So they're saying as long as this temperature range is small and the heat capacity doesn't change much across that range, then this is a reasonable equation, okay, or a reasonable way of estimating the change in internal energy or enthalpy. Now, if you notice, if you go to the back of your book and you look up any of the solids or liquids that they've got, and I can't give you a reference, you really don't have to go there if you don't have to. If you look up a heat capacity for solid or liquid, they will always report C sub P. They will report the heat capacity at constant pressure. The reason they do that is because it's actually extremely difficult to take water, for example, which is in its liquid phase, add energy to it, yet prevent its volume from changing. Okay? Because the water is going to push very, very hard. Okay? It's kind of like when, it's not the same, but it's kind of like when you have a phase change and water goes from solid or from liquid to solid, you can bust a pipe open. Well, there can be a significant pressure buildup if you take water in a pipe, has nowhere to go and you increase its temperature. It's going to press on that pipe very, very hard. So controlling that water and preventing it from expanding while you add thermal energy to see how its temperature changes is very difficult, and you get almost exactly the same result as if you hadn't constrained its volume, because this volume doesn't change enough to have a significant boundary work addition. So anyway, let's see. Oh, so we can do one more thing with this. We had essentially this stuff from the last slide, and we have delta H equals delta U plus V delta P. If we don't cross this off, if we say we're going to leave it in here, it turns out we can actually use this for something that's really effective. Go to the back of your book, please, the saturation tables. And we'll just use saturated liquid water. That should be fine. And just, I guess to keep this clear, let's go to the metric tables, not the English tables. Okay? Now, if you wanted the enthalpy of water at, let's say, a pressure of 101 kPa and a temperature of, let's say, 50 degrees Celsius, would you be able to find that in the table? No. Why not? Because this is so cool. Think about it. I gave you atmospheric pressure and a temperature below boiling. So this is a subcooled liquid, right? That is a table for saturated liquid. Now in 220, what we always did when we needed a property at some conditions that was subcooled, we didn't have a table of subcooled liquids, so what we did is we said the pressure doesn't affect it much, so I will simply look up the enthalpy of saturated liquid at 50 degrees, because the properties are more dependent on temperature than they are pressure. Okay? So what you would do is you go to the saturated table, you look up HF, at 50 degrees Celsius, and you would approximate the enthalpy that you really want by this HF. Okay? Now we can improve on that. We can do a little bit more. We can include the effective pressure. Now when students first see this, it kind of blows their mind. They don't understand what it's talking about. But let me help you out here. What I'm going to do is show you how this equation will help us do better than just this. So go ahead and give me the number. Look up 50 degrees Celsius.
209.34.
209.34, okay. I'm going to change colors because the red seems to be red. So 209.34 kilojoules per kilogram. Okay, so there's the estimate for enthalpy at these conditions, and we're just basing it on the temperature. Now, we don't really want that. What we really want is the enthalpy at a pressure and temperature. The pressure and temperature are 101 kilopascals, 50 degrees Celsius. Now, if you think about it, we could use this equation, since this is a difference in enthalpy between 2 points, and a difference in internal energy between 2 points, and a difference in pressure between 2 points. We can use this equation to come up with a better estimate for the enthalpy at PT by doing this. So watch what happens here. Basically, what we have to do is look up the enthalpy of saturated liquid at temperature, which we have. This would be our normal estimate. But now we can add on this correction factor. So notice what I've got. P and T, what are they? Well, P is 101 kPa. That's the particular pressure that I'm interested in. T is 50 degrees Celsius. We have already looked up HF at T, right? We've got that piece. Now look up the specific volume at that same temperature, the specific volume of saturated liquid. So what we want is V sub F at 50 degrees C. I'm sorry.
0.001012.
Thank you. And that's cubic meters per kilogram. And then what do? Well, we multiply that specific volume by the pressure difference. What pressure difference? The pressure of interest less the saturation pressure at the temperature. Okay? So what we're going to do is approximate this as 209.34 kilojoules per kilogram plus the specific volume 0.001012 cubic meters per kilogram multiplied by the actual temperature, the actual pressure, which is 101 kilopascals, less the saturation temperature. So what is the saturation temperature?
Saturation pressure.
Saturation pressure at 50 degrees Celsius. It's how much?
12.35.
And that's kPa, right?
Yes.
Okay. Now, grab your calculators, take 101, subtract 12 or so. The 0.352 is probably not all that important. Okay. So take that difference and then multiply it by 0.001, and let's get the magnitude of this term.
0.0897.
0.0897. Okay, and the units, we have to be a little bit careful here. The cubic meter times the kilopascal is a kilojoule, so sure enough, this is kilojoules per kilogram. This is not a very big correction for this, is it? So most of the time, you are justified in neglecting it. But if you really need a more accurate answer, you can do this. Okay? So the enthalpy is a little bit higher than it should be because the pressure is a little bit higher. Okay? And that's why we took the pressure difference here. So this would only change, technically this decimal place, but since it's going to roll over, this is like 0.09, then that's going to change this. So that the result would be 209 point, what, 433, yeah. Kilojoules per kilogram. Okay, so we can do a little bit better. Now let me warn you guys, this is nice to know, okay? You can see that it's really unnecessary because it changes so little. So this is kind of a red herring. This is not really the point of the chapter, but this is something that can be useful. Okay? Now it turns out that in our book we also have tables of compressed liquid water. We didn't have that in 220. Let me show it to you. And if I got lucky and chose a good point, then we'll be able to compare our estimate here to what they have in the water table. Saturated water table, they put it in an odd order because they have saturated, then superheated, and then compressed liquids. It's page 922. And of course, I won't be able to do it. I should have chosen 5 megapascals or so in order to get on these charts and compare. But if you wanted to, you could use this equation, run through this again basically, and end up with a point that actually is in the table and see how close it gets you. Okay? All right. Now, if there is no change in pressure, if there's no difference in pressure, then basically your change in enthalpy will be C delta T. If delta T is 0, then your delta H would be V delta P. In other words, if you have a process where the pressure is not changing, then the change in energy of the liquid or solid, whatever it is the heat capacity times the change in temperature. But if there's essentially no change in temperature of the fluid, but there is a change in pressure, then the change in energy is basically the specific volume multiplied by the pressure difference. Now, this is not quite so foreign to you, okay? This you've used before when you tried to calculate, well, even when we had the brass plate, right? We used that equation essentially. All that was changing was the temperature. And so to quantify the energy deposited into the plate, we used C delta T. Now, you've all had fluids classes, right? In fluids classes, do you assume any temperature change of the fluid? Only when you're talking about inefficiency, right? When you first start off, you're pretending that everything is 100% efficient. You have a hydraulic motor. What does it do? Well, it changes fluid power into rotational power. Or you have a pump. What does it do? It changes rotational power into fluid power, right? And you always have this V delta P term, which represents the energy change in the flowing stream in the fluid. Okay? Now, if there's a temperature change, then you know that there's some inefficiency as well that you have to account for. But essentially, these two pieces can account. Usually, one will be small by comparison to the other. Okay? In this class, most of the time, this is the one we're interested in. In fluids, you're usually interested in this one. Okay?
Wait a minute.
Yeah, please.
If the change in P equals 0,
Then the change in energy, essentially, of the solid and the liquid is given by, it is represented by the change in temperature. So, for example, let me give you some
okay.
examples.
No, I got that. So you're
Okay.
saying if there's no change in pressure, then the change in temperature is what's driving the
That's
change
how the
in
energy is being stored.
Yeah.
Right.
Okay. And vice versa.
Right, so if you've got a hydraulic fluid and it's not changing its temperature, but its pressure increases, then the energy added to that stream is basically VdP.
And that V is specific.
That's specific volume, yes. Yeah, and notice for a hydraulic fluid, its specific volume doesn't change a whole lot, even when you put a decent amount of pressure on it. Okay.
Thank you.
No problem, thank you for the question. I like questions. Okay, we have finished off chapter 4. Chapter 5, there's some parts that are familiar to you in chapter 5, especially mass balances. The end of chapter 5 is more difficult than anything you've seen in 220 before because it is unsteady energy balances. So we can have things changing with time, like mass flowing in or out and energy flowing in or out. Okay? So we haven't dealt with that kind of problem. We will get to it later. I just wanted you to know that it's coming. But we have about 30 minutes left. I'll give you a full 30 minutes. You guys, are you ready to take the quizam? All right.